Hey everybody, we're picking up here on week 4, day 2. Just going to be a continuation of what we had been talking about on Monday, which was the wind. So I'm not doing this content from home, but I'm doing it from the office today, and I'll push it out in just a little bit. And so what we were talking about, we had just to recap this, we had the 3 situations where the vessel was moving ahead, vessel was stopped, vessel was moving astern. As we come down, stopped, moving ahead, and astern. Remember, I talked about it was all about the L word. That wasn't loser. It was about leverage. And so we got this wind speed of 15 knots, and it is blowing on directly on the side of the ship. The upper case here, the first case, no headway or sternway, we've got equal leverage, equal force for and after the pivot point, we would have lateral motion. This one, we would have longitudinal motion because the vessel is moving ahead. We're going to have lateral motion, wind's blowing on the side of the ship, and there's going to be rotational motion around the pivot point as well. It's the difference in the amount of work which is happening here, the amount of force, the amount of effect of that wind after the pivot point compared to forward of the pivot point. We change it up, we're going astern, it just reverses, and it's a similar situation. Remember, I did say that a vessel, most vessels, if not all vessels, will to a degree, and they'll be to different degrees depending on the configuration of the ship. They will seek the wind, left up to their own devices when they're moving ahead, and it's most notable when it's a gentle movement ahead. And it will also seek the wind when moving astern. It will back into the wind, or it will head up into the wind. There is a formula that I want to give you, and write this down. There it is, point 004, that's a constant. And then we get the capital W, that is windage, that's the wind area or the sail area, given to us in square feet. And then the V, lowercase v, that's expressed for velocity squared. All of that, 0.004 times the square footage times the velocity squared, all divided by 2240. Absolutely, this is going to be on the test. I'm going to ask you to do some numbers and to do it correctly, but let's work through it. So I'll just leave that on there for a minute, and then we'll go on to the next slide. All right, now, before we start to apply that, let's talk about sail area. Let's talk about that windage. That means the same thing. So we got this car carrier, Wallenius lines, and we've got a tanker here that's in a ballast condition, a lot of freeboard. That tanker could be in a low condition, and you wouldn't have as much freeboard. You wouldn't have as much windage area. And then we go to a container ship, a Triple E class. This is a vessel which is came out about 5 or 6 years ago, and the sheer amount of not only just the freeboard, but those containers stacked up on deck. We kind of talked about that a little bit in class. Then there's a tug and a barge, and this looks like the barge might be in a light condition, and so hence a lot of freeboard. Well, here's an example. We're going to simplify that barge, and we're going to make it 300 feet by a 45-foot beam, 300-foot length. All right, here's the bow of the barge, here's the stern of the barge, and we've got a 12-foot freeboard. So the only numbers that we really care about is the 300 and the 12. Let's see, 300 by 12. That's 3,600 square feet of surface area that the wind could hit on. Let's assume that the wind is hitting directly on the port side. That's right here. We're looking at the port side of this barge, and it's hitting directly on the port side at whatever wind speed we got. So let's give it a wind speed. Let's say we've got a 10-knot wind speed. And so I'll apply the formula, decimal 004, times the square footage of the wind surface, the steel surface there. That is the length times the freeboard, and then times the wind speed squared. Right, so 10 squared, all of it divided by 2,240, which I think I mentioned, or you should know, is the number of pounds in a long ton. So we deal with long tons quite a bit. And the wind force comes out, we solve that formula, and it comes out to be 0.6 tons. And frankly, you don't have much of appreciation of what 0.6 tons is. I could create a situation where I could suspend 0.6 tons on a cable or a line from a tree or something, or from the overhead, and I could encourage you to walk underneath it. And that might make you appreciate it. But, all kidding aside, that's not going to give you enough to really understand what these forces are. But for right now, just remember, it's 0.6 tons. Well, okay, so quickly you look at this, and I'm going to increase it to a 30 knot wind speed. So same formula, but the wind speed changes. And it comes up, and now it's 5.8 tons. Well, that's a big deal. But still, what's 5.8 tons? What does that translate to? What is that? I mean, how do you make that into real life? I realize if I said to you, I'm going to suspend, 0.6 tons on a rope above your head and make you walk underneath it, and then I said, well, I'm going to put 5.8 tons, you'd probably be a little bit more nervous about that. Yeah, I get that. You understand that 0.6 is not as significant as 5.8. But when it comes to things that, forces affecting vessels, whatever vessel that might be, that might not just resonate with you enough yet. I'm going to try to give you something. I'm going to try to teach you something now. So when it comes to force, and we've used this term, that 100 horsepower equals 1 ton of bollard pull. We talked about that last class. That was on the test. Okay, roger that. We good. We got it. All right, the Pentagoet, our tugboat, delivers 18 tons of work. In other words, we would say in the business, 18 tons of bollard pull, BP. But you could also think of that, by the way, as bollard push. It's just the work that the Pentagoet can do. So here's the deal, and remember this. That is a new unit of measurement. A new unit of measurement. 1 Pentagoet. Instead of saying 0.6 tons or 5.8 tons or whatever, we're going to say how much of a Pentagoet. Let's go back for a minute. Let's go back here. So this one had, with the wind blowing on the beam, it was 5.8 tons. Let's just round that off a little bit. Let's just call it 6 tons, all right? We can do that. All right. How much force can the Pentagoet deliver? 18 tons. That's 1 Pentagoet. That's what it can do. So this is about 6 tons compared to 18 tons. This is about 1/3 of a Pentagoet. Well, yeah, okay, now all of a sudden, if you think like me, all of a sudden we kind of got a comparison, something to work with there. If I took the Pentagoet and I put it on this barge and I had it pushing on the side of the barge, we're looking at the starboard side, we're looking at the port side here. What if I put the barge, back, put the tug back on the starboard? What I'm saying is that 1/3 of the Pentagoet's power pushing towards me over on the starboard side would equalize the wind force that's hitting on the port side. You see what I'm saying? It's just a way of thinking about it. It would take 1/3 of the Pentagoet's power to handle this barge if there was a 30 knot wind on it. Okay, well now we've made some progress. And that's what I call a Pentagoet. Now we're going to keep thinking about this Pentagoet here. So let's take a ship that looks like this, whatever it is, a bulk carrier or a tanker. It's got an 800-foot length and a 16-foot freeboard. Got that? 800 feet long, much bigger ship, not the barge anymore, 16-foot freeboard. So we're going to take that same formula, the constant times the square footage area, and we'll have a 10-knot wind, and we run it out. So when the wind is blowing on the port side of this ship, all up and down here, but we'll come back just thinking of it right there at that point of action. It's 2.3 tons of force. The question I'm asking you is, can the Pentagoet handle that? If you put the Pentagoet on the opposite side of the ship, on the starboard side of the vessel, and you throttled up with the Pentagoet, could you keep this ship in position with the wind blowing at 10 knots on this side, the port side, right towards the ship? Could the Pentagoet on the other side throttle up? Yeah, of course it could. Of course it could. It would be a challenge maybe to find so that no twisting of the ship occurred, but theoretically you could do that. Okay, so stay with me now. The same ship, we were 10 knots. What do we have, 2.3 tons? And now we've got a 30-knot wind. Take the same formula, it's the same ship, the constant, there's the sail area, the windage area, but now 30 knots, 30 squared. We run the arithmetic. This isn't math, this is arithmetic. All right, that means if we've got a wind blowing on the port side of this ship, hitting the above the waterline area, that wind generates 21 tons of force. Okay, this is the aha moment. The Pentagoet, you, captain, on the Pentagoet, are screwed. You don't have enough horsepower, you don't have enough bollard power, bollard push, bollard pull, whatever you want to call it, to compensate, because you've only got 18 tons to push back against that 21 tons of wind force on the port side. You're going to lose control of the ship. And now you can start to understand that. Got it? What's our unit of measurement? It's a Pentagoet. Fully throttled up. What's the Pentagoet got to work with? It's got 18 tons of force. If you've got 21 tons of wind force on that ship on one side and you put the Pentagoet on the other side, you're not in good shape. So now, in a matter of probably about 5 minutes, we've gone from really not understanding what a ton of force or 5.8 tons of force or 2.3, now we understand we can call it a Pentagoet. I'm going to ask you that question. Be ready for that. What is our new unit of measurement? Talk to your lab instructors about that. If you have Captain Leach or any of the other guys who are really familiar, the people who are familiar with the Pentagoet, they'll like that discussion. So you see what I did? I didn't just change the color of the ship from purple to blue. I put containers on deck. So now we've got a wind force. I've got my area of the ship. I've got a 20-foot freeboard plus a 18,000 square feet of containers here. That's going to give me 16,000 plus 18,000, and then I use the 30-knot wind, and look what we got here. Now we got a container ship with a big stack of containers on it. This is not a huge container ship. This is an 800-footer. This is a kind of by today's standards, this is a small container ship. The bottom line is that generates that wind operating on the port side of this vessel, striking it all up and down here. That's going to generate 54.6. How many Pentagoets do you need? Let's see, Pentagoets, 18, 2 Pentagoets is 36, 3 Pentagoets, 30, 46, yeah, maybe 3 Pentagoets, right? Perfect, you got it. It would take 3 Pentagoets to be able to, and you would just barely be able to hold it against that wind of a 30-knot wind on the port side if the Pentagoets were all lined up, 3 of them in a row. That's pretty good, isn't it? That's pretty good. That's a pretty good way of thinking about it. So I hope that is good for you, and I hope that resonates. So what are we looking at? We're looking at running water. Our next topic of discussion is going to be current. And so we're going to have to look at the current forces. How much How is this different than wind forces? That's what we're going to get into. Okay, so now, it's going to be the current. Obviously, similar. As a matter of fact, you can see here we have a similar formula, not exactly the same, but fairly close. And we can approximate, or we can get a pretty good guess of the magnitude, or what does the current do to us, and how does that compare to wind? So what we're looking at is to calculate the load exerted by the current on the beam. Same situation, just like we were talking about the wind operating on the beam on a stationary vessel. This is a little bit more to it because we got an extra factor that we're going to put in here. So the current load in tons equals, the length in feet of the water line. We got the mean draft, so that's going to be L times D. The velocity, speed of the current, there's times V squared. And then we have this new one that's right here. I don't mean to make this confusing, by the way, I've ordered it this way, but the under keel clearance factor, I wanted to talk about this last. So current load, we take the under keel clearance factor, I'll show you those in a minute, and we've got the times the length of the water line by the draft, right? That's going to be the square footage area of the hull underwater. And then again, times velocity squared is exponential velocity here. All right, so just wanted to pause for a minute to let you capture that. You should be writing this down in your notes. You certainly should you have access to the PowerPoint in Canvas to go on, but to supplement, just watching the video here. Let's look at this. Here's our factors that we talk about. Here's that in that formula. So the F would be 0.0015, or we would use a factor of decimal 0018 or decimal 0036, and it's a function of what is the UKC. So this is as we think about UKC, in this particular slide here, we would be using something. We have a real constriction underneath here. Right? We have a real constriction of, we're running very, very close to the bottom. You imagine, if you will, the current is running in this direction, hits the side of the ship. It can't squeeze under the vessel easily as it could when you were in deeper water. And that's why we're going to use different factors. Let's go back here. We're going to use different factors when you think about the under keel clearance, whatever it is. Whenever the under keel clearance isn't very much, you're going to use one factor. When you've got a lot of under keel clearance, you're going to use a different factor. What is that factor going to be? So this is what you want to write down. When the depth of the water is 3 times the draft. Now think about that. So when the depth of the water is 3 times the draft. If the water depth of 60 and your draft was 20, that would be the water depth as 3 times the draft. And the water would not be constrained like we're seeing it here. All right, so 60 and 20. 20 is the draft, and 60 is the depth of the water. So that would be, you would use this factor. If you had a draft of 20 feet and you had a water depth of 40 feet, that would be 2 times. Then you would factor in this one right here. Let's see. if you had a draft of 20 feet? Well, that's what this image illustrates. If you had a draft of 20 feet, there's the draft. And if you had a water depth of 22 feet, let's see, that would be when depth is 1.1 times the draft. The draft is 20, the water depth is 22, yep, that's 1.1 times the draft. Then you would have to use this factor, decimal 0036, and you'd have to plug this in. That's going to change things dramatically, and we'll watch how that happens. All right, so here we have a vessel. It has a 1 knot current striking it on the beam on the port side. What is the force exerted by the current? It has a draft of 32 feet. It has a length at the water line of 650 feet, and it's got a water depth of 65. Let's see, 32-foot draft, 65-foot water draft. That's close enough to saying it's going to be twice the draft. 32 and 32, that's close enough to saying 65. We won't split. We won't worry about that too much. So here's our situation. We got a 1 knot of beam current. It's operating on the port side. It's hitting all of this underwater area here. We know the formula because it is 2 times the draft. That's our water depth. It's 2 times the draft. It's a 65-foot water depth. There's our length, and there's our draft, 650 feet long, 32-foot draft, 1 knot current, so that's velocity squared. So we run the numbers, that's 37 tons. 1 knot exerts 37 tons of force. You get it? They're big numbers. And the question or the thought that should have come to your head, if we're talking about 37 tons of force striking this vessel on the port side caused by what's happening here underwater, how many Pentagoets is that? It's 2 Pentagoets, give or take, right? You need to have 2 Pentagoets just for a 1 knot current. I'll tell you what, this is a good example, and you're upperclassmen, you've seen the state of Maine come and go, I think, in general, you've seen that. We come and go, we leave Castine on slack water, we don't go when the Pentagoet is flowing at all, because we don't want to get broadside to the current as we spin the ship around. We don't want to take any risk at all, because that force of that current hitting the underwater profile of the ship is huge numbers. And in a pretty small harbor, that could be detrimental. I mean, those would be, and even though we wait for slack water, think about that. And we have a couple of tractor tugs and the Pentagoet. We don't take any chances. It's big, big numbers here. We were talking about a 1 knot current, and what about a 2 knot current? I mean, the difference between a 1 knot current and a 2 knot current, you say, big deal, it's not that big a deal. Yeah, it is. With a 1 knot current, we ended up with 37 tons. We take the same ship, we go to a 2 knot current. You see what I mean? We get to a number of 150 tons. Holy smokes. 150 tons. How many Pentagoets? How many? You know what I mean. Anyway, so I'm kind of playing with this, and I'm giving you some thoughts to think about. But So how many pentagoets is that? Let's take 150. I'm pulling the calculator out, and I'm just going to divide 150 tons of force with a 2-knot current. I'm having a hard time getting my calculator out here. But I'll do the math for you. 150 divided by 18, yeah, that is 8.3 pentagoets. Well, you can't have a third of a pentagoet, so we'll call it 9 pentagoets. That you'd have to have 9 pentagoets on the side of that ship, on the side of this vessel. This one right here. You know, that's only the 32-foot draft, and it's only 650 at the waterline. Whew. Incredible forces, people. So I want you to appreciate that. It's only when you think about the force of the Pentagoet that you really, that you can start to understand that. But it gets worse. But wait. So here's the same situation, but now you've got a 2-knot current and you have a water depth of 36 feet. So do this one on your own. But think about it. We're going to use, now we're down to that larger factor there. Remember the 3 factors we had for the under keel clearance? Now we've got we basically got a water depth of 1.1 times the draft, and so we get here and we got 0.36. We run the same numbers here, and that's 300 tons. 300 tons of force with a 2-knot current and very little under keel clearance, which, by the way, so we're using this number, and the reason is because you've got very little under keel clearance here. You've got very little UKC, and this current is flowing, and we're trying to take another vessel and put it over here, Pentagoets, and we're trying to push back on this side, and the current's flowing on this side. I know it's not something that you would probably ever do, but as a way of thinking about it, it's helpful. It's because of this squeeze here, and the water cannot flow freely, so all of the impact hitting this underwater portion of the hull. It's all, it can't go anywhere else. It can't spread out around the vessel. It can't go under the vessel. So that's why we have this big increase. Those are huge numbers. 300 tons of current force. 9 pentagoets. Holy smokes. No, did I say that wrong? 17 pentagoets. 17 pentagoets. That's what that equals right there. 300 tons, 299.52.